that's already done. However, I used no planes of symmetry in that particular problem. What I would like to do in this segment, I would like to repeat that same problem, except that there will be a plane of symmetry, which is, if you look at this, this drawing, which is the YZ plane of symmetry. I also want to remind you that although it looks like, but the XY is not the plane of symmetry of this problem, because notice that the type of load on the that is applied to this on the top and the bottom are different. The top, in the top situation over here, there is a hole and the surface of the hole is strained, clamped. In the bottom portion, there is no hole, and also it's given a different type of restraint. In other words, the entire face is required to move downward by thousandths of an inch. So XY, strictly speaking, is not a plane of symmetry. If I was displacing this thing up by a thousandth of an inch, and this one down by a thousandth of an inch, and there was no hole here, or there was a hole at the bottom, then of course XY would also be a plane of symmetry. Okay, I'm not going to generate the model here. That was already done in Catia, so let me go back. This was already done. So all I'm going to do is I'm going to split it in the middle to get half of it made. So let's see now. Here's the split, and this is the plane that I would like to use, and there it is. This is half of the thickness of the original problem. The material is already there, so why don't we go ahead and move to the generative structure analysis. And let me remind you how I refined the mesh in this area, although this refinement is not done in the book, at least in this chapter, but it's so easy that we might as well do it here. So you look at the Model Manager toolbar right there. You look at the second toolbar, sub-toolbar, and it says Local Mesh Size. So I click on it. It says, what is the support? The support is this. And all that means is that the elements that are here, that are associated with the surface, are going to have a smaller size. So why don't I make this thing 1/10 of an inch? See how it's going to look like. So there it is. You can see that in this part of the model, the elements are that size. In the rest of the model, this is the default size. So if you look at the mesh, this is what you got. Okay? Very good. Let's deactivate the mesh. While we are at it, let us go and save all these things. First of all, I want to remind you that the part, obviously you have to save, because on a test you have to submit that part. You also have to save and submit the analysis file, which is not done automatically. If you go to File, Save Management, you notice that there is a part here that I need to save, and there is also the analysis file that needs to be saved. So let me select the analysis file, save as. Let me go on the desktop. I create a new folder. This is C-clamp. Okay. All right. So not only the part is going to be there, the analysis part is going to be there also. Good. So let's see now. What we need to do is we have to apply the restraint. The restraints are the interior surface of this hole is clamped, okay, and this plane, which was the plane of symmetry, I can put surface slider on it. I also want to remind you that the meaning of the surface slider is that there is no displacement perpendicular to that flat face. The alternative way, if you don't want to use surface slider, is to say that there is no displacement in this direction, which happens to be x in the present drawing. Good. The next thing we want to do is we want to take that face and move it down by 1/1000 of an inch. Okay. Now, if you go to back to the first segment, I said that if you want to specify a non-zero displacement, first you have to specify a zero displacement, and then you can change it. So you go to the user define, on that face, in the direction z, zero, direction z is direction 3. And now that I have this, I can go and use the enforced displacement right there in the load, because that's kind of a load that we're applying, although staying in context of a displacement. Enforced displacement on that face, and you can put the value that you want, the thousandths of an inch. Just be careful. Do not take a thousandth of an inch and divide it by 2, because this is a displacement. It doesn't matter whether you took half of the model or the whole model. If I gave you the force, because you're taking half of the model, then you apply half of that force, but not for displacement. Okay, so let us run this. Look at the deformation. This is exactly what you expect and what you experience in the case without the symmetry. If you look at the stress distribution, von Mises stress distribution, and let me actually change the rendering here so that you can see it. All right, this is good. Now, notice that still there is patchy stuff here, so either I can go and change the size. Let me go and change the size. How about to 0.05 and run it? It'll take longer, but let's see how it's going to look like if we make the size there smaller. Done. So let's look at the stress again. It looks a little bit better. Now, I cannot change my element type, but if I could, because of my graphics card, I can go and make this one parabolic, and a lot of these things are going to go away. All right. Now, let me deactivate this plot. Okay. Now, suppose I want to know how much force is needed to make this bottom face move down by 1,000ths of an inch. If you go to the first segment, you see that I've done this. So I go to Sensor, right click, create Resultant Sensor, create Reaction Sensor. Just wait for a second. Okay, now I'm expected to find a restraint. I have two choices. I can select this restraint, the one that I gave it a 0 displacement and I changed it to 0.001. This is what I did in the first segment. Or I can select the restraint up here. You know, as far as the reaction force is concerned, you're going to get the same values in opposite direction. So why don't I just go ahead and do it just like I did in the first video clip. So I select this, and then I say update results. Notice we are getting minus 3.59 pounds in the downward direction. Now, in order to move this thing down, you have to apply a downward force, and that's why you have negative. And notice that the value is exactly half of what I got in the first segment. That shouldn't surprise you, because in the first segment, I did not use a plane of symmetry. Both pieces on the two sides of the plane of symmetry were present. And obviously, to move that face down by 1,000ths of an inch, you need double of what you're seeing right now. So be careful. This is the kind of mistake that can easily be done on a test. So we say okay. All right. Now I still have some time left. So suppose that I have the same problem with only one minor change, and the minor change is that I actually have a hole. I don't have a hole on the top. Okay. Suppose I don't have the hole on the top. Okay, so how would that change the problem? If I don't have the hole in the top, and I know I was told that the two faces These are the faces. No hole on the top. So let me erase this. No hole here. And I was told that the two faces are moved down a thousandth of an inch here and a thousandth of an inch there. Now you can see that XY is a plane of symmetry. So in order for us to do this problem, all we need to do is to model 1/8 of this part. So I want to do that for you. Let's go ahead to our Catia model. Actually, I'm going to kill this. So Catia model, I'm going to first of all delete that sketch, the circle in that sketch. Delete, exit. Then I'm going to cut it, split it with that horizontal face, XY face. Keep the top part. Now I go to generative structure analysis. And, if you want, you can refine the mesh there. But, I'm not, all right, let's actually do that. So let's refine it in that segment, 0.05. If you look at the mesh, as you expect, you get a fine mesh in that area, and then the rest of it is as you want. Deactivate this mesh. Okay, so we have surface slider on the side. This was a plane of symmetry, and at the bottom, this is a plane of symmetry. We can apply this thing separately or at the same time. Now we're going to give it a zero displacement upward as we have done in the past. Now we can change it. A thousandth of an inch, what is it? A thousandth of an inch. This obviously is going to be, because of the piece that I picked, it's going to be plus. Let's run it. Okay, notice that first of all, we have a problem here. I told you in class, if you know how to fix this, go ahead. If you don't, then maybe you can ask Catia to tell you what the problem may be. So I'm plotting the deformation and I'm animating it. There's animation right there. And you can see that this piece is free to move as a rigid body in the direction 1. Okay, so we have to prevent that rigid body motion. So why don't I go ahead here and deactivate this, we'll delete it. Now we're going to take a user-defined restraint at a single point and prevent that rigid body motion, and rigid body motion was not in direction Z, it was in direction Y or direction 2. Actually, yeah, that's fine. That's fine. Right. So let's run it. This could have been, by the way, any other corner points. Let's look at it. There. And this is exactly the kind of thing that we got before. Now you can see that the rigid body motion is taken away right there. All right, so this was the second video segment of the 3 that I'm going to do. The next one is going to be dealing with introducing beam elements to you. All right.